RMO 2024. Problem 6. Let n be a positive integer greater than or equal to 2. We define an n chain as a sequence of integers 1 equals a1, less than a2, less than a3, and so on up to ak equals n, where each term divides the next term. That is, a1 divides a2, a2 divides a3, and so on. Every step in the chain multiplies by some integer factor greater than or equal to 2. The chain must start at 1 and end at n. The chain can have any number of steps in between. Let's see all chains for a small example. N equals 4. The problem tells us f of 4 equals 2. The two 4 chains are: first, 1 then 4. This is valid because 1 divides 4. Second, 1 then 2 then 4. Valid because 1 divides 2 and 2 divides 4. What about 1 then 3 then 4? No, 3 does not divide 4. So this is not valid. What about 1 then 2 then 3 then 4? No, 3 does not divide 4. So exactly two valid chains exist for n equals 4, confirming f of 4 equals 2. Let f of n be the number of n chains. F 2 equals 1, f 4 equals 2, f 6 equals 3, f 8 equals 4, f 12 equals 8, f 24 equals 20. For numbers of the form 2 to the m times 3, f 6 equals 3, f 12 equals 8, f 24 equals 20. The formula claims f of 2 caret m times 3 equals 2 caret m1 times m plus 2. The key is the prime factorization structure. Every divisor of n equals 2 caret m times 3 has the form 2 caret a times 3 caret b, where b is 0 or 1. Each step ratio equals 2 caret alpha times 3 caret beta, not both 0. The total power of 2 sums to m, and the total power of 3 sums to 1. So exactly one step contributes a factor of 3. Here is the complete problem statement. Let n be a positive integer at least 2. Call a sequence 1 equals a1 less than a2 less than ... less than ak equals n and n chain if each ai divides ai plus 1. Let f of n be the number of n chains. Prove that f of 2 to the m times 3 equals 2 to the m minus 1 times m plus 2 for every positive integer m. Let's now prove this step by step. Step 1. Encode each chain by the step ratios. Each ratio a underscore I plus 1 over underscore I equals 2 caret b underscore I times 3 caret c underscore I. With b underscore I and c underscore I non-negative and not both 0. The total power of 2, sum of b underscore I equals m. The total power of 3, sum of c underscore I equals 1. So exactly one step has c underscore j equals 1. All others have c underscore I equals 0. Step 2. The single 3-step divides chains into two types. In any valid chain, exactly one step involves multiplying by 3. At that step, the ratio is 2 to the b underscore j times 3 for some j. This 3-step can occur in two different ways. Type A. The 3-step also involves a positive power of 2. That is, b underscore j is at least 1 at the step where c underscore j equals 1. Type B. The 3-step is a pure step multiplying only by 3. That is, b underscore j equals 0 at the step where c underscore j equals 1. This classification is the key to the counting argument. Step 3. Introduce compositions of m. A composition of M is an ordered list of positive integers that sum to M. For example, the compositions of 3 are 3, 1, 2, 2, 1, and 1, 1, 1. An L-part composition of M has exactly L parts. The number of L-part compositions of M equals C. M1, L1, by the stars and bars formula. The total number of compositions of M is 2 to the m-1. Compositions are the key tool because the b_i values at the PURE2 steps form exactly a composition of M. Step 4. For each L-part composition of M, count the chains. Fix a composition x1, x2, xl of M with L parts. This composition determines the b_i values at the PURE2 steps. The 3-step can be inserted in 2 ways. Type A, at one of the existing L steps, merged with a 2 power. This gives L choices, 1 for each step. Type B, as a brand new pure 3-step inserted at one of the L+1 gaps. Before step 1, between step 1 and 2, or after step L. This gives L+1 choices. Total chains from this composition. L plus L plus 1 equals 2L plus 1. Step 5. Detailed construction of type A chains. Given L-part composition x1, x2, xl of M, choose one index j from 1 to L. At step j, the ratio is 2 to the x_j times 3. At all other steps I not equal j, the ratio is 2 to the x_i. The chain visits 1, then 2 caret x1, then 2 caret x1 plus x2, and so on. But at step j it also multiplies by 3. This gives exactly L valid type A chains. Each chain has exactly L steps total. Step 6. Detailed construction of type B chains. Again take L-part composition x1, xl of M. Choose a position j from 1 to L plus 1 to insert the pure 3-step. If j equals 1, insert times 3 at the very beginning. If j equals I for 1 less than I at most L, insert times 3 between step I-1 and step I. If j equals L plus 1, insert times 3 at the very end. This gives a chain with L plus 1 steps total. All other steps remain pure powers of 2 from the composition. This yields L plus 1 type B chains per composition. Step 7. Set up the total count as a sum. The n chains are in bijection with pairs. Composition of M. Choice of where to put the 3-step. For each L-part composition, we get 2 L plus 1 chains. The number of L-part compositions of M is C. M1, L1. So the total count is F 2 caret M times 3 equals the sum from L equals 1 to M of C. M1, L1 times 2 L plus 1. This is the key formula we need to evaluate. Step 8. Evaluate the sum. Substitute j equals L minus 1, sum of C. M1, j, times 2j plus 3, split into 2 times sum of j times C. M1, j, plus 3 times sum of C. M1, j. The second sum equals 2 caret M1. By the binomial theorem, the first uses j times C. M1, j, equals M1 times C. M2, j1, giving M1 times 2 caret M2, total M1 times 2 caret M1 plus 3 times 2 caret M1 equals 2 caret M1 times M plus 2 QED. Complete proof summary. Every 2 carat m times 3 chain corresponds to a composition of m together with a placement of the single 3 step. For an L part composition, there are L type A chains and L plus 1 type B chains, giving 2 L plus 1 total. Summing over all compositions, f of 2 carat m times 3 equals the sum of C m1 L1 times 2 L plus 1. Substituting j equals L minus 1 and splitting the sum gives m1 times 2 carat m1 plus 3 times 2 carat m1, which equals 2 carat m1 times m plus 2 QED.